Welcome everybody to this week's Green Bank Community Zoom. I'm Jim Jackson. Just a few announcements about what's going on at the observatory. I'd like to welcome our new staff scientist, Annika Schmiedeke, who joins us from Germany. Annika works on star formation. I'm really excited to be able to work with her, and she's going to bring a lot of expertise, particularly at high frequency observations, to the observatory. Semester 22B proposals have been through their subpanels. The remaining steps are to have the TAC meeting where all the results are compared, and then a director's review. So stay tuned for that, but you should be hearing from us about your proposals for 22B in second week of May or so. All right, our last call for large proposals or low frequencies was quite successful. We got about 20 proposals and we accepted about 12 of those. So many of you have started observing those large programs already. So thank you for your interest, and there's some really good science there. Summer maintenance will be starting in a couple months. This summer, we're going to be tackling some painting on the saddle clamps, and we've hired a company to do that. And they're also going to be doing some testing of a sandblasting and coating method with the aim toward a large proposal to NSF to paint the entire Green Bank telescope. Ultra wideband receiver, I showed some results last time. The initial tests were very successful. Did uncover a few issues. It's back in the lab. It will go back up on the telescope. We're planning to resume testing the ultra wideband receiver in June. All right, well, that's all from me. I'll hand it off now to Jay Lockman, who will introduce today's speaker.
Thanks very much, Jim. Today's speaker is Karen Perez from Columbia University, speaking about breakthrough listen search for intelligent life near the Galactic Center. Let me remind everyone to submit your questions through the Q&A box at the lower right, and we'll go through them at the end of the talk. Take it away, Karen.
Okay. Hi everyone. Thanks for inviting me. So yes, my name is Karen Perez. I'm a third-year grad student at Columbia, studying pulsars at different wavelengths. And I also work with the Breakthrough Listen team and Vishal Gayar over at UC Berkeley on the search for intelligent life using various radio telescopes. And today I'll be talking about looking for this intelligent life specifically near the Galactic Center, following some preliminary results from our survey, which you can also see in our 2021 paper. So Breakthrough Listen is the largest ever research program aimed to find evidence of civilizations beyond Earth. And the Galactic Center survey aims to cover the widest radio frequency range ever to look for intelligent life and look for both narrowband signals and broadband signals. And the reason why we're looking towards the Galactic Center is because the line of sight towards it has the highest concentration and highest density of stars in any given direction in the sky. It's also a potential location for an intentional beacon built by Advanced Intelligence, and it's also the most energetic region in the Milky Way. So due to the inside-out formation of our galaxy, stars near the center or closer to the Galactic Center have had a longer time to develop habitable planets, and consequently, these habitable planets have also had a longer time to develop intelligent life. So if you look at this plot in the bottom left, as we move towards the Galactic Center, you can see that about 10% of stars have at least one habitable planet. The second point is this idea, the Schelling point idea from game theory, which says that if you have a set of two people, or in this case, two civilizations, and they are trying to communicate, and they don't know how, there should be a common solution. So for example, if you're in New York City with a friend and you're trying to meet them and you don't know what time or where the most common solution to that problem is that you would probably meet them at noon at Grand Central Station. So similarly, we can take a similar approach and use this idea of the Schelling point theory, the Schelling point idea to search for intelligent life, because we have such a broad range to search in, and we have to narrow it down somehow. And the obvious common solution to this would be the galactic center, because it is the center of our galaxy. So it's naturally a common point for an advanced civilization to put a beacon, because it would maximize its chance of detection across the sky. Similarly, another example is if you have like 4 quadrants and you were to tell someone to choose one, they would most likely choose the first one, because that's just kind of natural. So various surveys have been done in the past, including like Shostak and Tartar. They've conducted a 4-hour search for narrowband signals, and they specifically only looked at the 21 centimeter hydrogen line. So surveys that have been done in the past are relatively short in observation time, and they also cover very narrow bandwidths. So our survey is different in the sense that it will be the first survey to cover a wide range of bandwidths at a high sensitivity, and we will produce high resolution data products to search through. So we will be using both the Parkes telescope in Australia and the Green Bank telescope to cover this wide range from 700 megahertz to 93 gigahertz for a total of over 600 observing hours. And so far we've observed and conducted analyses on about 19 hours, so 11 hours with the Green Bank telescope and 9 hours with the Parkes telescope. So we will be using the ultra wideband receiver from the Parkes telescope to cover our lower end of the frequency range, and then we will use 7 different bands from the Green Bank to cover like the rest of the 90 gigahertz. So for each band, we will have both deep galactic center bulge pointings, and these typically be used for broadband signals, whether that be from astrophysical sources or artificial signals. Then we will also have shorter 5-minute pointings, and these shorter 5-minute pointings will be used to look for narrowband signals. So far we've finished C-band. We only need 2 more hours of long observations to conduct, but we've done the entire analyses on the rest of it, and we've covered the first 14 pointings of the Parkes telescope. And I'll show these pointings in a bit. So here we have the C-band pointings. We have 19 pointings in total, and A00 denotes the galactic center. So like I said earlier, we're doing these 5-minute observations, and we're using an on-off strategy. So if you look at this C-band here, the idea is that we would look, for example, at A00, the galactic center, for 5 minutes, and then we would point to C01 for 5 minutes. And we would just alternate between those two, and we would have 6 pointings in total. So we would have 3 observations on A00 and then 3 observations on C01. And we want to make sure to keep these observations a beam width away to accidentally avoid any double detections. So similarly for the Parkes observing plan, the green, this dotted circle around the green section denotes like our galactic center bulge, where A1 is the galactic center. And again, we want to have an off counterpart. So in this scenario, the off counterpart to A1 would be B1 up here, because we also want to make sure that we stay a beam width away. So again, for like A2, the counterpart would be B2, A3, B3, and so on. And these are the 14 pointings that we've covered in our first section of our survey so far. So how do we go about looking for these narrowband signals? Well, we use TurboSETI, which is a breakthrough listen code to look for narrowband Doppler drifting signals. And like I said earlier, we have such a broad parameter space to search in, but because it's very computationally expensive, we use an SNR of 20 and a drift rate of plus or minus 4 hertz per second. So ideally, we would want to search at much higher drift rates, but we are limited by computational expenses. So before I get to the latter part of this, of what this pipeline does, first I just want to show you the number of hits that we get before we go onto candidates. So running TurboStudy through our data, you can see that this histogram is showing you the number of hits across frequency ranges. So in total, between the Green Bank telescope and the Parkes telescope, we have almost 2 million hits. So just to show you the distribution of them. So now how do we go from these hits to actually classifying signals? And especially how do we differentiate between like Earth-based signals, radio frequency interference, RFI, and other signals, whether that be from satellites or something else. So the way that we do this is, like I said earlier, we point at a source for 5 minutes, and then we point away from the source for another 5 minutes, and we repeat this 3 different times. So ideally, this is what a ideal ET signal would look like. It would appear on all of the on observations, but none of the off. This would tell us that it's not Earth-based interference, that it's actually coming from outer space. And the other thing that we look for is that it's non-zero drifting. So you can see here the signal has a non-zero drift rate. For RFI, because it's Earth-based, it would have a 0 drift rate, and it would actually appear as a straight vertical line, and it would appear in all of our observations, not just every other observation. So this is what an ideal signal would look like. It would be showing up on all 3 ons, and it would be drifting across time. So now we get to the latter part of our TurboStudy pipeline. So now that we know how to do this on-off comparison, we can go ahead and find any candidates from the hits that we previously had. So we can go ahead and remove any candidates that have 0 drift rate. Like I said, these are most likely RFI. And then we can also go ahead and filter out our candidates by filter 2s and filter 3s. So filter 2 candidates are candidates that are seen in at least 1 on observation, and filter 3 candidates are those that were seen in all 3 on observations. So then we can go ahead and plot our events and just visually inspect them to kind of identify any interesting signals. And I will go through some of the plots next. But first, I want to show you some histograms. So this is a histogram showing the number of events that we found across different frequencies. They're kind of plotted by filter 2s and filter 3s. So in the blue and the orange, you can see the filter 2 candidates, which means that they were seen in at least 1 of the on observations. You can see that there's a lot of orange and blue. And then the black and the red shows you the candidates that were seen that passed filter 3, which means that they were seen in all 3 of the on observations. And there's not a lot of these. You can see a few red here, some black back here in the 4 gigahertz frequency line. And then I want you to pay attention to this candidate that I circled here in green. You can see that it's kind of isolated from the rest. There's not really any other candidates near these frequency ranges, and it also only has 1 candidate at this frequency, as opposed to all the others that seem to have more than 1. Here is our drift rate distribution. So you can see that it peaks around 0. And this is because even though we did remove all the candidates that had a 0 drift rate, we did not move those that were very close to 0. So this is something that we will keep in mind in the future to avoid having to do additional visual inspection for plots that are very obviously RFI. This is our drift rate scatter plot. So these are all of our candidates at the drift rate that they were detected and the frequency that they were detected. And a plot like this is just useful to see, like kind of identify what frequencies have RFI, or if we have a candidate that's interesting, we can go back and look at this plot and see how like prominent the RFI was. So now we can look at some examples. So these are some examples of RFI. The plot on the left is very clearly RFI. Like I said earlier, the signal shows up on all 6 observations, and it also has a very low drift rate, close to 0. The plot on the right, oh, sorry, I should also mention that these two candidates were found with the Green Bank telescope. So C05 is from the C-band observation, the 5th pointing So the plot on the right, we're looking at this triplet pattern right here. This one is also rejected as RFI because it only shows up on one of the on observations and none of the other on observations, and the drift rate is also very close to 0. And if we look at other frequencies, this triplet pattern appears again. So this is at frequency 4.11, and the plot on the left is 4.19, and you again see this triplet pattern, and this triplet pattern also appears onto the off pointing. So this is very clearly RFI, probably some intermittent Earth-based source. So this is what an ideal candidate would look like. This candidate, you see, this was found with the Parkes telescope, our B2 pointing. This candidate is seen in all 3 on observations only, and it's also drifting across time. So this is what an ideal signal would look like, what we expect an ideal signal to look like. But unfortunately, if you look up 1.38 gigahertz, you will find that it's actually a GPS satellite called Napstar. But yes, this is a good plot just to showcase what we're looking for essentially. Then we had 2 really interesting candidates. These were also detected with our green bank pointings, C03 and C09. And I can go back to that plot later if you want to see exactly where that's located. So our plot on the left, we can see that we detected a signal with like a relatively high drift rate. But again, this can also be rejected because it was only found in one of the on observations and none of the other on observations. Also, we can see that this was detected at 4.1 gigahertz. And if we go back to our frequency distribution plot from earlier, we can see around 4.1 gigahertz. There's a lot of candidates here. So it's not really unique like this one in the green circle that I showed earlier. So going back to this one is around 6.4 gigahertz. And this is actually the other interesting candidate that we found. So here we go, 6.4 gigahertz. This also has a relatively high drift rate. But because this source was only detected in one of the ons, we also rejected as RFI. And it probably, again, being due to some intermittent Earth-based source. The last thing I wanted to talk about was these wideband signals. So as opposed to narrowband signals, which was the rest of my talk, we're also looking for wideband signals. So obviously this covers a much wider frequency range than narrowband signals. So things like pulsars, astrophysical sources produce these wideband signals. So you can see in this first plot here, pulsars have a positive dispersion measure. So this is what a frequency versus time plot will look like if you plot the data. And the idea is that if an advanced intelligence exists and they know of these astrophysical sources, they might try and produce artificial signals to kind of differentiate those signals from astrophysical sources. So these signals could be flipped across frequency or flipped across time or flipped across both frequency and time. And my mentor Vishal Gayar produced a pipeline called Spanda to search for these. So we, after the first 19 hours of our observations, we haven't found anything yet, either wideband or narrowband signals, but we are only 3% into our survey. So we still have many more hours to complete. And our C-band observations and analysis have been complete. Like I said, we only need 2 more hours of deep observations to go. And then X and K-band observations will follow this summer. And even though we have not found anything yet, I think it is just interesting to note that new pipelines are constantly being developed, and people are starting to deploy machine learning methods and other interesting techniques to search through our data. So even if we don't find anything now, this is data that will be continued to look at for years and decades to come as new analysis techniques are developed. Yeah, and if you want to read more details about our paper, you can check it out. Yeah, and I'll take any questions now. Thanks.
Thanks very much, Karen, for a most interesting talk. It's quite possible that your talk contains more bits of data than any other one that has previously been given. Let me remind everyone to enter questions through the Q&A box on the lower right, and we have a few right now. What is the criteria for finding civilization? It's a pretty broad question.
I guess if we're talking about intelligent life here, the idea is that we're looking for a beacon, so like intentional transmission of signals, like deliberately transmitting signals. So the idea is that if there's another civilization out there that has a radio telescope, they might try and to make themselves known, right? So they would be deliberately transmitting these signals. Yes, I think that's the best way to answer that question.
Okay, here's another question. I can generalize it by saying there have been speculations that there are specific frequencies that would be preferred, like multiples of the 21 centimeter line frequency. Have you done searches at specific frequencies like this?
I have not done specific searches at the 21 centimeter line. I know other searches have, like I said earlier, Shostak and Tartar did a 4-hour narrowband search at the 21 centimeter line. But I think that's been done a lot in previous surveys. And I think the purpose of the survey is just to go beyond that. Like we've already looked there, haven't found anything. And there's such a wide range of frequencies to cover. And this is what this survey is trying to do, not limit ourselves to one specific frequency range.
Mm-hmm. Okay, thank you.
So we will cover that within our survey. That is included.
Are most of the candidates turn out to be interference from satellites or terrestrial sources? Or do you even know?
So yes, I think we do know that. I think candidates that pass our filter 2s and filter 3s are more likely to be satellites, just because, like I said earlier, those are candidates that would only appear on the ONS. So those are probably more likely to be satellites. But then our candidates that don't pass those filters are most likely to be Earth-based sources. So we are trying to filter out those Earth-based sources. So yeah.
Okay. Do you use wavelet analysis?
I don't believe that we do.
Are the observations being recorded in a way that will allow larger drift rates to be searched for with future computing resources?
Yes, they are. So yes, we are constantly working on pipelines to like increase the searches that we are able to make, and these observations will eventually become publicly available, so anyone can also go ahead and search through the data at the parameters that they wish.
Okay. If you find interesting signals, is there a way to estimate the distance over which they've traveled?
I'm not sure about that. I'm not sure if we're recording all. Oh, I guess, let me think. I think there would be a way to know the distance that, I mean, we obviously know, we don't know how far the distance is maybe, but I think we know where we're pointing at. So we know how far we are from where the signal is, I guess, if that was the question.
Yeah, that's a fascinating question. I'm not sure that there is a good answer to that.
Yeah.
Are there beacons on Earth that might give other civilizations indication that there's life on this planet?
I guess we have like various radio telescopes, right? And I guess our Arecibo telescope is kind of the pioneer for SETI. So I guess we do have certain beacons that other civilizations might be looking to us for. And I guess we also have satellites and things like that. So assuming that other civilizations are more intelligent than us and can detect our satellites, I guess you could consider those to be beacons as well.
Okay, let's see. I've messed up the questions here. Okay, will breakthrough listen extend beyond 2025?
I am not sure about that, but the hope is that it will be. I think we're making a lot of progress, and there's a lot of surveys that just started and need to be completed, such as this one. So I think we're very hopeful that it will be continued beyond that.
Okay, and you said that your observations of the Galactic Center, is it the observations are 3% complete, or the reduction is 3%?
Oh, the analysis is 3% complete. The observations themselves, we probably have more like 5 or 7% complete. Yes, we started some of the X-band observations, and we've done some more of the parks observations, but we haven't really processed the data yet or done the analyses.
Yeah, but so you still have most of the data has yet to be taken on the Galactic Center.
Yes, that's correct.
Yeah. Mm-hmm. Okay, are there any other questions? Well, if not, I would like to thank everyone for attending this most interesting presentation. I'd like to remind you that the presentation has been recorded and is available on the Green Bank Observatory website under the science category. Please join us again in 2 weeks for the next in this series. On April 27th, Jeffrey Hasbun of the University of Washington will report on monitoring the solar wind with pulsar timing observations. We look forward to seeing you then. Thanks and bye.